I had an idea. What if I used a Quest 3 VR headset as the head of a robot? Turns out, it actually works. And in this video, I'm going to show you how I built it, from the hardware to the software to the AI that lets me talk to it. After some research, I built this prototype turtle robot using Lego, some common electronics components, and of course, the Meta Quest 3.
Destination reached.
Here's a quick demo.
Fridge.
Going to fridge.
The Quest headset acts as both the brain and sensors of the robot. It sends movement commands over Wi-Fi to an onboard ESP32 microcontroller, which then drives the DC motors.
Waypoint.
And here's the best part. The Quest 3 has built-in spatial mapping and positional tracking thanks to its cameras and depth sensors. This means the robot can understand where it is in the room and plan routes around obstacles, all without needing any additional sensors, like LiDAR for example.
Waypoint.
Now let me show you how I achieved all of this. The first thing I set about doing was building the actual robot. Since the project is more of a proof of concept, I built the chassis out of Lego. I mounted the Quest 3 headset on top of this chassis, but made sure it was easily detachable. Let me remove the headset from the robot so you can see the chassis and the electronics more clearly. The robot is a two-wheeled turtle bot with a geared-down DC motor driving each wheel. These motors are controlled by an ESP32 microcontroller via an L298N motor driver. This motor driver is what's known as an H-bridge, which allows the ESP32 to control the direction and speed of the motors while isolating the low-power microcontroller from the high-current motor circuit. Okay, let me show you a schematic of the whole circuit so you can see how all of the electronic components work together. The whole thing is powered by 6 AA batteries providing a total of 9 volts. The battery pack feeds directly into the L298N motor driver. You'll notice that the motors are connected directly to this driver, as well as a number of digital output pins from the ESP32 chip. One useful feature of the L298N is its 5-volt output. I've taken advantage of this to power the ESP32. We can consider the Lego chassis with its electronic components to be the body of the robot. The Quest 3 acts as the brain and sensor array of the robot, so we can consider this to be its head. And so, the next thing I set about doing was getting the head to communicate with the body. As far as I'm aware, there's no easy way to achieve communication between the Quest and a microcontroller via USB. However, my ESP32 chip, the DevKit C variant, has built-in Wi-Fi. So I decided to use wireless UDP for my robot's head-to-body communication. If you're wondering what UDP is, it stands for User Datagram Protocol. It's a fast, lightweight way to send data over a network. It prioritizes speed over reliability, which I thought would make it more suitable for my project, since I wanted the robot to respond quickly, even if that meant occasionally missing a command. So how did I set up UDP communication between the Quest 3 and the ESP32 chip? Let's start with the ESP32 side. The ESP32 runs a simple program that I wrote and uploaded using the Arduino IDE. Let's take a look at it now. At the top of the program, I include a couple of libraries that enable Wi-Fi network communication. Directly below, I define some variables for my home Wi-Fi credentials. In the setup function, the ESP32 connects to my Wi-Fi network and starts a UDP server listening on port 3310. The main loop is simple. It continuously checks for incoming UDP packets. When a packet arrives, the ESP32 reads a single command byte. This command byte is processed in the apply command function. Let's take a quick look at it. Each command byte uses 4 bits to set the state of 4 GPIO pins, specifically pins 16 through 19. A 0 bit sets the corresponding pin to low, and conversely, a 1 bit sets the pin to high. These pins connect directly to the L298N motor driver, and their states control the direction of each motor. This way I can get the robot to move forward, turn, or stop. Motor speed is controlled separately using PWM on pin 25, which connects to both enable pins on the L298N. Okay, so the robot's body is ready to receive commands. Now let's move on to its head, the Quest 3. This is the device that will ultimately be sending commands to the ESP32 chip. For the Quest headset, I used Unity to create an application that gives the robot the ability to navigate around a room autonomously. As you have seen in my quick demo, you can say the name of a predetermined location in the room, and the robot will navigate to it. Let's open the Unity project and see how it works. Okay, I have this robot scene open, which is the only scene that I use in this app. If you look at the scene hierarchy, you will see a game object called Robot Controller. This is the main game object in the scene, as it's where all the key components of this application are attached. Let's select it. In the inspector, you can see that Robot Controller has several scripts or components attached to it. Each script handles a different aspect of the robot's functionality. To make things clearer, I've created this chart showing the responsibility of each script and how they fit into the larger whole. The Robot Controller orchestrates all of these subsystems. It is also responsible for handling user input. I am currently using the MetaQuest's touch controllers to do certain things with the robot. For instance, I use them to set location markers around the room. I can also use the controller's thumbsticks to gain manual control over the robot. Anyhow, I would like to complete our discussion about UDP communication. Therefore, let's take a look at the ESP32 Communicator script next. This is the component responsible for sending motor commands from the Quest 3 to the ESP32 chip over Wi-Fi. If you look at the inspector, you can see I've configured it with the ESP32's IP address and UDP port number. Let's take a quick look at the script. The first thing we do in the start method is initialize the UDP client, creating a communication channel with the ESP32 chip. This ESP32 communicator will mostly be used by another component called Robot Navigation, which we'll look at later. The Robot Navigation component decides when the robot needs to execute various actions, such as moving forward, stopping, or turning left or right. To communicate these actions, Robot Navigation calls the setCommandGivenAction method, passing in the desired action. This action is then passed to the getCommandGivenAction method, which converts it into a single command byte using the same bit pattern we saw earlier in the Arduino code. This byte is then sent via UDP to the ESP32. Okay, let us now move on to another key component in this application, the Location Anchor Manager. This component manages spatial anchors, which are essentially persistent 3D markers that I can place around my room. Each anchor represents a specific location, like the fridge, the sofa, or the table. These anchors use the Quest 3's spatial anchor system, so they persist between sessions and stay locked to their real-world positions. Each anchor has a label assigned to it. When I give a voice command like "go to the fridge," the Location Anchor Manager finds the anchor labeled "fridge" and tells the robot where to navigate. I use the touch controllers to place these anchors by pointing at a surface and pressing the grip trigger. I can then assign a label to each anchor, and once I'm happy with my arrangement, I can save it for the robot to use. So now that we've covered how the robot knows where to go using spatial anchors, let's talk about how it actually gets there. That's where the Robot Navigation component comes in. Robot Navigation handles pathfinding and decides what actions the robot needs to take, whether that's turning towards a waypoint, moving forward, or stopping. It's implemented as a state machine that coordinates all aspects of autonomous navigation. But in order to navigate autonomously, the robot needs to be aware of its environment. This is where Meta's spatial mapping comes into play. If we look at the scene hierarchy, you'll notice there's a component called Scene Navigation. This is part of Meta's Mixed Reality Utility Kit, or MRUK for short. What Scene Navigation does is take the spatial data from a room scan, all the walls, furniture, and obstacles the Quest 3 has mapped, and converts it into a Unity nav mesh. Robot Navigation then uses this nav mesh to calculate safe paths, determining where the robot can drive and where obstacles need to be avoided. Anyway, let's take another look at the Robot Navigation script. Let's see how this state machine actually works. When a destination is set, Robot navigation calculates a path using the nav mesh and breaks it down into waypoints. The robot then navigates toward each waypoint following a simple cycle. The deciding state determines whether to move forward or turn. The turning state rotates the robot to face the waypoint, and the moving state drives forward. Between each action, there's a paused state that waits for the robot to physically settle. The motors don't stop instantly, so the robot can coast a bit. The paused state monitors the robot's rotation and waits for the robot to come to a standstill. This cycle repeats for each waypoint until the robot reaches its destination. Now, before we move on, let me show you how robot navigation uses the ESP32 Communicator to command the ESP32 chip, and by extension, the robot's motors. Let's take the moving state as an example. When the moving state is active, it calls the ESP32 Communicator's setCommandGivenAction method, passing in the action move forward. The ESP32 Communicator then sends the corresponding byte command, in this case 0101, to the ESP32 chip. Okay. The final piece of the robot control puzzle is speech recognition, the system that lets me control the robot using voice commands. This is handled by two components working together, the mic recorder and run whisper scripts. If we return to the Unity editor, you can see that the mic recorder is one of the scripts attached to the robot controller. However, I've placed the run whisper script on its own game object of the same name. These two components are linked together through direct references, allowing them to communicate with one another. Anyhow, this is how the two components work together to interpret my voice commands. The mic recorder component continuously listens to the Quest's microphone, waiting for me to speak. When it detects the start of speech, it records the audio. Once I stop speaking and there's silence, it extracts that portion of audio and passes it to the Run Whisper component. Run Whisper is where the AI comes in. It runs an on-device whisper model, a speech-to-text AI from OpenAI. I am using the tiny variant, which is small enough to run locally on the Quest 3, albeit with some noticeable lag. The audio goes through an AI pipeline, first converted to a spectrogram, then encoded, and finally decoded into text. This pipeline has been implemented using Unity's inference engine, which is an API for running AI models on device. Incidentally, I've already implemented this exact speech-to-text system in a previous project, which I cover in my video, Offline Speech Recognition on MetaQuest. So, if you want more detail on how this whisper speech recognition system works in Unity, I recommend checking that out. Anyway, back to our brief overview. Once the whisper speech-to-text transcription is complete, the final step is very straightforward. This takes place in Run Whisper's understand instruction state. The script simply scans the text string for specific keywords such as fridge, sofa, or table. When it finds a match, it dispatches an instruction event which is handled by the robot controller. From here we tell the location anchor manager to find the nearest anchor with the same label and set it as the destination. So that covers the important components on the software side. Now, I want to show you a couple of important things about the hardware setup. First, the Quest 3's built-in microphone isn't really adequate for this project. I had to have my face right next to the robot for my voice commands to be detected. Therefore, I decided to use an external wireless mic. I went for the Soundeus Lavalier wireless mic. It's fairly cheap and it works well for this project. Here you can see the receiver attached to the Quest's USB port. You can find a link to this mic in the description. Next, we need to talk about the Quest's proximity sensor. The Quest 3 has a sensor that detects when the headset is being worn, and when it's not on your face, it automatically puts itself to sleep to save battery. Obviously, this is a problem when the headset is mounted on the robot. I simply taped over the proximity sensor with a strip of electrical tape. This tricks the headset into thinking it's constantly being worn, so it stays active and keeps running the application. Admittedly, this is a bit hacky, so in the next phase of my project, I will try to disable the sensor in software. One final thing I would strongly recommend. I didn't do this in my demo, but if you wish to recreate my project, I would urge you to cover the headset's lenses. The reason is that the lenses can act as a magnifying glass. Direct sunlight can focus through them and damage the internal screens. And with that, a quick disclaimer. If you decide to build your own version of this project, please do so at your own risk. I can't be held responsible for any damage to equipment. Okay, so I think I have covered all the important aspects of this project. It's been a really fun project combining VR hardware, Unity development, AI speech recognition, and robotics. This is still very much a work in progress. In future iterations, I'd like to improve navigation smoothness, maybe add real-time obstacle avoidance using the Quest's depth sensors, or maybe even implement some basic object recognition. There are a lot of directions in which I could take this project. If you have some suggestions, please leave a comment below. In any case, my next step is to clean up this project and then make it available for download, most likely on GitHub. I'll let you know when it's ready, so if you want to stay in the loop and get notified, please consider subscribing. Anyway, thank you for watching, and I'll see you in the next one.